You know that specific feeling of relief when you walk into a coffee shop or maybe a new office and you crack open your laptop and the Wi-Fi icon just connects.
Oh, yeah. It's the modern version of a sigh of relief. You're plugged in.
Right, you're part of the hive mind again.
Exactly.
And it feels completely automatic. But I was looking through the source material for today's deep dive, specifically these technical certification guides on implementing DHCP and securing Layer 2. And it turns out that magic is actually a really high-stakes negotiation.
Yeah, happening in milliseconds. It is surprisingly bureaucratic, actually.
It really is.
It's less like magic and more like a very rapid, very precise legal proceeding. You know, there are contracts signed, leases granted, identities verified.
And that is exactly what we are going to audit today. We are looking at the invisible hand that assigns your identity on the network, which is a protocol called DHCP.
Right.
But we aren't just stopping at how it works. We're pivoting to the dark side of it. Because it turns out this process is incredibly easy to hijack.
It is. The protocol was built in a totally different era, an era of trust.
Right.
And if you don't have the right security guards in place, that split-second connection is exactly when a bad actor can steal your data without you ever knowing it's happening.
So the mission for today is twofold. First, we want to unpack the handshake that actually gets us online. And second, to understand the bouncers, specifically DHCP snooping and dynamic ARP inspection that keep the bad guys out.
We're going from the absolute basics of connectivity straight to the architecture of trust.
Let's start with those basics. The host.
Okay.
In my head, a host is, someone throwing a dinner party. But in the context of these technical guides, the definition is a lot broader, isn't it?
Much broader. In the TCP/IP world, a host is simply any device that requires an IP address to participate in the network.
Which is everything now.
Exactly. Obviously, that's your laptop or your smartphone. But the sources point out things we usually just ignore. That digital billboard you walked past at the mall.
One playing the looped perfume ad.
Yeah, that's a host. The smart thermostat in your office, that's a host. Even the power meter on the side of a house.
Really?
Yeah, if it sends usage data back to the utility company over the internet, it's a host. And the key thing to remember here is that every single one of those devices, from a supercomputer down to that smart thermostat, needs 4 specific pieces of information to actually function on an IPv4 network.
Okay, I feel like I know the first one, the IP address.
That's the identity, yes. It's your unique ID card for that specific network.
Right.
But an IP address alone is actually pretty useless. You also need a subnet mask.
Which defines the boundaries of the neighborhood, right?
Precisely. The subnet mask tells the device, hey, these are the people you can shout to directly, and for everyone else, you need to go through the door.
And that door is the third piece, the default gateway.
Or the default router, yeah. Without that address, you're permanently trapped on your local network. You can talk to the printer down the hallway, but you can't get to Google or Netflix.
Because you don't know the way out.
Exactly. And finally, the fourth piece is the DNS server address.
The phone book. Because, I'm not typing in raw IP addresses to check my email.
Nobody is. You type a name, the DNS server gives you the number. So you have these 4 essentials. Identity, which is the IP. Boundaries, the mask. Exit, the gateway. And look up the DNS.
Got it.
Now, your laptop doesn't just guess these numbers. It has to ask for them. And this is where we get into the DORA dance.
DORA. This is the mnemonic for the handshake. I want to walk through this because the actual mechanics are quite clever.
It's a 4-step process. Imagine your laptop just woke up on a strange network. It has amnesia. It doesn't know who it is or where it is. So step 1 is D for discover.
Which is basically the laptop screaming into the void.
Literally, it sends a broadcast message to everyone on the wire saying, is there a DHCP server out there? I need an identity.
And then comes O for offer.
Right. A DHCP server hears that scream, checks its inventory, and replies, yes, I'm here. I have an IP address available, let's say 192.168.1.5, and here are the terms.
It's like a job offer.
Yeah.
But the client hasn't accepted it yet. That's step 3, right? R for request.
Yes. The client sees the offer and basically says, I accept. I would like to officially request that IP address, please.
And finally, A for acknowledgement.
The server stamps the paperwork, marks that IP as taken in its database so it doesn't hand it to anyone else, and sends the final confirmation to the client.
Discover, offer, request, acknowledgement. DORA.
You got it.
It seems straightforward, but the source material highlights a really interesting technical paradox here. The chicken and egg problem.
Oh, this is a classic networking interview question.
Right, because if my laptop doesn't have an IP address yet, how can it send a message asking for one? You need a return address to send mail, don't you?
You usually do. The engineers who designed this had to create a workaround.
What do they do?
Since the client has no identity, it uses the unspecified address as its source. That's 0.0.0.0 surround. It's the network equivalent of signing a letter anonymous.
And who does it mail it to? Because it doesn't know the server's address either.
So it mails it to everybody. It uses the local broadcast address, which is 255.255.255.255. It's essentially standing on a chair and shouting to the entire room.
Okay, so from nobody to everybody.
Exactly.
That works if the DHCP server is sitting right there in the same room or the same local area network. But here's what got my eye in the reading. Usually, routers are designed to kill broadcasts.
They have to. If routers forwarded every broadcast message, the entire internet would be completely clogged with, to everybody, junk mail. Routers are designed to stop broadcasts at the border of the local network. They are the boundary line.
So we have a huge problem then. If I'm in a branch office in Seattle,
Right.
and the corporate DHCP server is all the way in New York, my Discover shout hits the local router and just dies. It never reaches New York. I never get an IP.
That would be the default behavior, yes. But obviously, enterprise networks actually work. So network engineers use a specific tool called a relay agent.
The IP helper address.
That's the command syntax on Cisco gear, yes. You type IP helper address on the router interface that faces the clients, and it changes the rules of the game for that specific interface.
How does it change the rules?
It tells the router, look, I know you usually drop broadcasts, but if you see a DHCC broadcast specifically looking for port 67, I want you to catch it. Don't drop it. Instead, wrap it inside a new envelope, a unicast packet, and mail it directly to this specific IP address in New York.
So the router acts as a translator.
It really does.
It takes the screaming broadcast from the laptop, turns it into a polite direct message to the server in New York, gets the reply, and then translates it back to a broadcast for the laptop.
Exactly. It bridges the gap between the local broadcast domain and the remote server. Without that helper address, centralized DHCP simply wouldn't exist. We'd need a server in every single closet in every single building, which is just a massive management nightmare.
Okay, so the handshake works. We're connected. But before we get to the security flaws, let's talk about verification. If I'm debugging a connection or just curious, how do you see the receipts of this transaction?
Well, if you're on Windows, you've probably run ipconfig. But the real gold is ipconfig all.
I feel like tech support has made me type that 1,000 times.
It's the bread and butter. It shows you the physical MC address, the IP you got, the gateway, and the DNS servers. But crucially for our topic, it shows the lease obtained and lease expires timestamps.
Right, because it's a lease. You don't actually own that IP.
Never. Efficient networks need to recycle addresses when you leave.
Makes sense.
And if you're on a Mac or Linux, you're looking at ifconfig or the newer ipaddress command. The data is exactly the same. It proves the door I dance happened.
There was one quirky detail in the notes about routers acting as clients. We usually think of the router as the boss, right? The one giving out the IPs. But they can be clients too.
Think about your home internet. Your Wi-Fi router connects to the ISP. To Comcast or AT&T, your router is just a client. It has to ask for an IP just like your phone asks your router.
So it's do or a all the way down.
It is, and the source material mentions a really specific behavior for Cisco routers here. When a router acts as a DHCP client, it usually receives a default gateway from the ISP. The router installs this as a default route so it knows how to send traffic to the internet.
Okay, standard procedure.
But it assigns that route an administrative distance of 254.
254. Wait, isn't the scale usually 0 to 255?
Yes, and in routing logic, lower is better. It represents trustworthiness. A route you type in manually has a distance of 1 that's very trusted. A dynamic protocol like OSPF is 1 in 10. A distance of 254 is practically saying, I do not trust this route at all.
So why install it if the router barely trusts it?
It's what we call a floating static route. It acts as a route of last resort. It basically tells the router, use this path from the DHCP server only if you absolutely have no other instructions.
I see.
It prevents the DHCP information from accidentally overwriting a more important route the engineer might have configured manually.
That's a fascinating safeguard. It's like a fail-safe to keep the engineer in control. Okay, so we have the system. It works. We get our IPs. But now we have to peel back the curtain. Because this whole door wrap process, this broadcasting and shouting, is built on a foundation of absolute trust.
And that is its fatal flaw. DHCP was designed in the 80s. The assumption was that everyone on the network was friendly, probably researchers at a university. There are no ID cards, no background checks.
Which brings us to the spurious server.
Yeah.
The rogue DHCP.
Right.
This sounds like a spy movie trope, but how does it actually play out in a real coffee shop?
It's deceptively simple. An attacker walks in, buys a coffee, and plugs a laptop into the network. They run a piece of software. There are plenty of free tools that do this that mimics a DHCP server.
So now there are two authorities in the room, the real router and the attacker.
Right. Now, you walk in and open your laptop. Your laptop sends that Discover broadcast. Is anyone out there?
And both servers hear me.
And both reply. It is literally a race. The client typically accepts the first offer it receives.
So if the attacker's laptop is faster than the store's router,
Which it often is.
I just accept the attacker's offer.
You do.
But wait, if I accept the attacker's offer, wouldn't I notice? Like, wouldn't my internet just stop working?
If the attacker is clumsy, yes. But a smart attacker performs a man-in-the-middle attack. They give you a valid IP address so you can actually connect. But for the default gateway, the exit door, they don't give you the real router's IP, they give you their laptop's IP address.
I see. So my computer thinks the attacker is the router.
Correct. You try to go to your bank's website, your packet goes to the attacker logs it, copies it, maybe tries to strip the encryption, and then forwards it to the real router.
So from my perspective, the page loads. I'm sipping my latte, completely unaware that my traffic is taking a detour through the guy at the next table.
Exactly. You are online, but you are compromised. And this isn't the only way to break DHCP. There's also the starvation attack.
That sounds dramatic.
It's a denial of service. The attacker spoofs thousands of fake MNC addresses, basically pretending to be 5,000 different people entering the room at once. They request an IP for every single one.
They just drain the pool.
Within seconds, the DHCP server has leased out every available address. Now, when a legitimate user walks in, you or me, the server says, sorry, we're full, no connection for you.
Okay, so we have a system that is easily tricked and easily overwhelmed. We need a bouncer.
Yes.
This is where DHCP snooping enters the picture.
Right. DHCP snooping is a feature you turn on at the switch level, the device that actually connects all the cables. It turns the switch from a passive mailman into an active security guard.
How does it distinguish between the good guys and the bad guys?
It uses a concept of trusted versus untrusted ports. As the network engineer, you map out the switch. You tell it, port 1 connects to the real corporate server. That is trusted.
And the ports that go to the wall jacks, the ones users plug into.
Those are marked untrusted, and the rule is incredibly simple. An untrusted port is never, ever allowed to send a DHCP offer.
That kills the rogue server instantly.
Stone dead. If the attacker plugs into a wall jack and tries to send an offer packet, the switch inspects it, sees it's a server message coming from an untrusted port, and just drops it. It doesn't even make it to your laptop.
Simple, but extremely effective. But the source material mentioned that snooping also protects the other side. It validates the client too. How does that work?
This is a bit more subtle. Remember that DHCP packet. Inside the data payload, there's a field called CHADDR client hardware address. That's the client saying, my MAC address is XYZ.
Okay, so that's inside the letter.
But the Ethernet envelope that carries that packet also has a source address on the outside. DHCP snooping checks to make sure they match.
It's checking if the ID inside the letter matches the return address on the envelope.
Exactly. Attackers often spoof one and not the other to hide their tracks or launch those starvation attacks. If they don't match, the switch drops the packet. It assumes you are lying about who you are.
And what about the starvation attack itself? The guy asking for 5,000 IPs.
That's handled by rate limiting. You can configure the untrusted ports to only allow a certain number of DHCP packets per second, say 5 or 10.
Which is plenty for a normal user.
A normal user sends 4 packets once for DORA, and then is quiet for hours. If a port suddenly sends 100 packets in a second, the switch knows it's an attack. It puts the port into an error-disabled state.
It shuts down the port physically. You're done. Get out.
Exactly. But here is the most important part of DHCP snooping. While it is doing all this filtering, it is also taking notes.
Taking notes.
It builds a database called the DHCP Snooping Binding Table.
The binding table. I saw this bolded everywhere in the text. It seems crucial.
It is the holy grail of Layer 2 security. Every time a legitimate DORA handshake completes on an untrusted port, the switch records the details. MC address A was assigned IP address B on VLAN 10, port 5.
It creates a verified guest list.
A dynamic, real-time map of who is who. And this table isn't just for record keeping, it is the absolute foundation for the next layer of defense, which is dynamic ARP inspection.
Right, because securing the IP assignment is only half the battle.
Yeah.
Once I have an IP, I have to use it. And that involves ARP.
Address resolution protocol. We've covered this before, but let's refresh. Switches and cables don't speak IP. They speak MLASI address. If I want to talk to the router, I know the router's IP is 192.168.1.1, but I need its MASI address to build the Ethernet frame to actually send the data.
So I send an ARP request who has 192.168.1.1. And the router replies, I do, here's my MASI.
That's normal operation. But just like DHCP, ARP is inherently trusting. It allows something called a gratuitous ARP.
Which is an unsolicited announcement.
Right. A device can just jump on the network and shout, hey, everyone, just an update. I am now 192.168.1.1.
And the other devices they just believe it.
They do. They update their internal ARP caches immediately. Oh, the router changed. Okay, I'll send my traffic to the new guy. This is ARP poisoning. It's another way to achieve that man-in-the-middle position, but it happens after the DHCP handshake.
So the rogue server attack tricks you when you arrive, and the ARP poisoning attack tricks you while you're eating lunch.
Perfectly put. It redirects traffic by lying about identity. And this is where dynamic ARP inspection, or DAI, saves the day.
How does DAI distinguish a lie from the truth, though? ARP doesn't have a central server.
It cheats. It looks at the answers in the back of the book, the DHCP snooping binding table we made earlier.
Ah, I see the connection now.
When an ARP reply comes from an untrusted port, DAI intercepts it. It effectively says, hold on, you are claiming to be IP 192.168.1.1 with MSC address XYZ.
It checks the list.
It checks the list. And if the binding table says, no, sorry, MSC address XYZ was assigned IP 192.168.1510 viri, then the switch knows you are lying.
It drops the packet.
It drops the packet and logs the attempt.
That is brilliant. It uses the proof from the first protocol DHCP to police the second protocol ARP. It basically creates a chain of custody for your identity.
That's the exact phrase, chain of custody. Without snooping building the table, DAI wouldn't work at all. There are two halves of the same shield. You snoop the handshake to build trust, and then you inspect the traffic to enforce the trust.
This really highlights something for me. We started this deep dive talking about magic connections. But the reality is that the internet was designed for connectivity, not security.
That's the fundamental tension in all of networking. The early architects just wanted things to work. They wanted devices to find each other easily. They didn't anticipate that we would eventually be doing our banking and running critical infrastructure on these same trusting protocols.
So we've had to bolt these defenses, snooping, DAI, rate limiting, on top of the old plumbing to make it safe.
Exactly. It's retrofitting security onto a friendly neighborhood system.
So for the listener who isn't a network engineer, what's the big takeaway here? Why should they care about binding tables?
I think the real takeaway is realizing that your digital security is entirely physical. We worry about strong passwords and phishing emails, and we should. But if the physical network you plug into isn't securing the handshake, if it's not verifying that the router is actually the router, then all your encryption might not even matter.
It's about securing the foundation.
Yeah.
You can't build a secure house on a swamp.
Pres-
Now, before we wrap up, I have a thought that's been nagging me. And looking at the source material, it seems to be a common headache for engineers actually implementing this.
What's that?
We've built this perfect security system based on the binding table. The switch learns who you are when you do the DHCP dance.
Correct.
But what about devices that don't use DHCP? What about the office printer or a legacy server or the security camera that has a static IP hard-coded into it?
The static devices.
They never send the DHCP requests. They
Right.
never do DORA, so they never get added to the binding table.
You are spotting the fatal flaw in the design.
So if I turn on dynamic ARP inspection and the printer tries to send a message,
The switch looked at the table, doesn't see the printer, and drops the traffic. The printer essentially disappears from the network.
that seems incredibly problematic.
It is the classic trade-off between security and usability. If you lock the doors too tight, your own family can't get in.
So how do engineers solve that? Do they just turn the security off?
Hopefully not. They have to manually create entries, access control lists, or ECLs to tell the switch, I know you didn't see this guy come in, but he's cool. Let him talk. It adds administrative burden. Every time you buy a new printer, you have to go update the list.
Which brings us to the final thought I want to leave with the listener. We're moving toward a world of zero trust security. But as we've seen today, mechanisms like DAI rely entirely on a list of known good.
Right.
If the future is billions of IoT devices, light bulbs, fridges, cars, many of which might need static configurations or unique setups. Does this model of snooping in tables actually scale? Or are we building a security prison that's just too hard to manage?
That is the big question. Complexity is the enemy of security, but right now, complexity is the only thing keeping the attackers out.
Something to chew on the next time you connect to public Wi-Fi. Give a little mental nod to the Dora dance and the bouncers keeping it safe. Thanks for taking this deep dive with us.
Stay curious and definitely watch your handshake.